Hello, everyone, and welcome to our Chapter 3 lecture. Today we're going to cover matter and energy. It's going to be a pretty intuitive chapter, I feel. So we're going to move through things pretty quickly. We're not going to have any problem solving for this. It's very conceptual. Just to remind you guys, we do have lab this week. Next week there will be a holiday, so we won't have lab. And then the following week we will have lab again and the exam for chapters 1 through 4. So this week we'll have a quiz and lab, mainly focusing on chapter 2. Nothing really on chapters 3 or 4, so really, mainly just the mathematics. So we're going to get in chapter 3. So the key things I want you to focus on as we go through this is physical properties of states. So states are solids, liquids, and gases. We'll talk a little bit more about that. How we classify matter. So we can classify matter in a couple ways. Most generically, we can classify things as pure substances or not pure substances. Then we're going to have physical and chemical changes as well as the properties that kind of describe these changes. And then we're going to have a couple calculations. We're going to have heat calculations, which are going to be most important, and then we'll also talk about conservation of energy and conservation of mass calculations as well that you'll see in the book. So first thing we want to talk about is that, like we've said, everything around you, everything you can interact with is matter. And this matter is made up of something. Anything that has mass and takes up space is matter. That's what we've said in the past. Now we're going to kind of break that down a little bit more and say this matter is made up of atoms. Everything that you can interact with, everything that we call matter, is made up of these tiny little atoms that we would see on the periodic table. And so, like we said, anything that occupies space and has mass can be defined as matter. We're also going to later on in this lecture just start defining matter as anything that's composed of atoms. That's not 100% true if you get into physics or higher level courses, but for our purposes, anything that's composed of atoms is matter. Anything that's not composed of atoms is not matter that we're concerned with or isn't matter at all. So electromagnetic waves, heat, electricity, magnetism, those things are not matter. All right, some examples of what are matter. Basically everything around you. So it may seem like the things around you, the bulk objects that we deal with, like a table or a piece of glass, might be one continuous object that has no individual units. But if we look at it in a small enough magnifying glass, we can see that it's composed of atoms. These atoms are also composed of electrons, which are negatively charged, protons, which are positively charged, and neutrons, which are neutral. We'll talk about these a little bit more in next chapter, but these are what compose atoms. Atoms are what make up our elements, which are what are on our periodic table. If we combine our atoms together, we get molecules. These molecules, we have a whole bunch of names for them. We call them chemicals, we call them compounds, we call them materials, substances. We're going to use a whole bunch of names for molecules, but we want to understand that, we're all talking about the same thing. Two or more atoms joined together in a specific arrangement. Which atoms are joined together and the arrangement that they take and the geometry of that arrangement is what determines their chemical properties and their physical properties. So if we were to look at an aluminum can, we could see that there's just these repeating layers of aluminum atoms. This is a specific type of organization that is very common in solids. You don't see this in liquid and gases, and we would call this a crystal lattice, this repeating ordered array of atoms or particles, or it could even be molecules, but in this case we're talking about atoms. In other cases, we have things like isopropyl alcohol, which we most commonly call rubbing alcohol. Chemists sometimes call it 2-propanol. These are all the same names, and they all represent this molecule that has one oxygen here in red, a whole bunch of hydrogens in white, and 3 carbons in black. You can't really see the 3 carbons. They're kind of clustered together and hidden in the 3 dimensions. But this is the shape of isopropanol. It is always going to have this structure, this arrangement of these atoms, and so we call that the law of constant composition. Atoms or molecules will always be the same no matter where they are in the universe. A hydrogen atom is always a hydrogen atom no matter what. And a molecule of water, or in this case, a molecule of isopropanol, is always going to be identical to any other molecule of isopropanol. So, with fancy technology, we're able to use electrons to actually image individual atoms. You don't need to be focused on STM. This is just a fancy type of electron microscopy. It's actually two types of microscopy combined together to give you one type of image. And so we can see individual atoms with this, which is pretty interesting. You know, NIST probably paid a lot of money to have this image made. But we can also use it to look at things that are actually useful in the world. So this is an imaging of DNA. Since DNA is thousands and thousands of molecules and atoms combined together, we don't have the same resolution as when we're just looking at single atoms. So we have to zoom out a lot, and we kind of lose some of the fine detail, but we can still use it to image this double helix nature. You can kind of see how one strand underweaves the other, and they form the general shape of DNA that we come to know and love. So we're going to talk about 3 states of matter. There are other states of matter. You may talk about them in your academic career. Only thing we're ever going to be concerned with are solids, liquids, and gases. And so we're probably most common or most familiar with water as a common chemical that has all 3 phases of matter that we would interact with. So solid water is ice. We call liquid water water because that's its most common form on Earth. And then in the gaseous state, we call it steam. So in general, water's a little funny. Water is one of the few compounds out there where the solid is actually less dense than the liquid. This is why ice floats on top of water. The most dense temperature for water is around 4 degrees Celsius. This is a very peculiar thing. Typically, as things turn to solids, their density remains constant, and that's the most dense form they can take. This is because ice or solids have very close packing between the molecules. So if you look here, all of the water molecules are locked in position. They can't move because they're locked in place. That's why solids break. Liquids and gases, you can't snap them. You can't break them. When you break a solid, you're actually severing the plane of one of these lattices. So we would call this a crystal lattice. If you were to apply enough energy to snap the intermolecular forces between these molecules, you could cause a break in the solid. Since these molecules are locked in place and they're so close together, they can't move. They just kind of vibrate back and forth. Water is in between solid, or liquid is in between solids and gas, in that the molecules are still very closely packed. You know, you can see a whole bunch of molecules compared to how many are over here. But they're able to slip past each other. And so they're not so tightly packed that they can't move around. They're still able to slip past each other and move around. That's why liquids form to their container, whereas solids have a generalized shape. Gases are on the other end of the spectrum, where they're incredibly far apart. They have so much energy in their physical state that they separate to an extreme degree. Because of this, they basically move about with no significant interaction, and they don't have a definite volume, they don't have a definite shape. So, solids, like we said, they're fixed in location, they have neighboring atoms that they kind of vibrate next to, but they can't move by each other. So we have 2 different types of solids. We have crystalline solids, which have some sort of crystal lattice. So you can see here the alternating layers of atoms that form a regular pattern. We would call this a crystalline solid that has a crystal lattice. We also have amorphous solids, which are solids that kind of just congeal or conglomerate together. They don't have any long order repeating pattern. If you zoom in on a very tight segment of it, you might see some type of pattern, but that's just an artifact of the randomness. If you look at the overall solid or a bulk section of the solid, there's no long order, no long range order. So an example of this would be crystalline solid would be tempered glass, your windshield glass. It breaks into millions of tiny regular pieces, whereas an amorphous solid would be your regular kitchenware that you drop it breaks into a whole bunch of random shards. The regular long ordered pattern and crystal lattice that occurs in most solids, what gives them these kind of geometric looking shapes. So nothing that you need to remember about that, but just kind of a cool explanation of something we see in nature often. Liquids. So liquids have a fixed volume. They'll take whatever shape of the container that they're put in, but you can't change the volume of them. You can't expand or contract how much volume the liquid takes up. We'll call this compressibility. Liquids and solids are not compressible. If you press on a liquid or solid, it might deform, it might change its shape if you apply enough pressure, but it's not going to change its volume. You'll never change its volume. A gas, on the other hand, has very similar properties to water in that, the molecules can move past each other. It'll take the shape of the container it's in, but it also doesn't have a definite volume. And this is because the gas molecules are so far apart that if you can contain them in a space, you can actually force them closer together. We call this compressibility. And so here's an example of a piston. You can compress down gases. More gas is harder to compress, or a solid is hard to compress because all of the particles are already touching. With a gas, we can compress them until they get to this arrangement. Now, that doesn't necessarily make them a solid, but it just would give that gas the same density of a solid. Once you release the piston, it would then go back to whatever its initial conditions were. So here's a good table to look at, just for memorizing all your properties of physical states. So just to reiterate, solids and liquids are very close together, whereas gases are far apart. This is what leads to their compressibility or incompressibility. Since liquids and solids are close together, we can't compress them. However, gases are far apart, so they are compressible. Solids are fixed in their location. They can't move past each other, and so they just vibrate. Since they're fixed in position, they have a definite shape, and since they're not compressible, they have a definite volume. Liquids are able to shift past each other, move freely, so they'll form to whatever vessel they have, so they don't have a definite shape, but they do have a definite volume. You can't compress them. And then gases are incredibly far apart. They're free to move however they want. They'll take the shape of any container, and they'll take the volume of whatever the container or conditions allow for. So now we're going to move into classifying substances. And so like we mentioned, you can classify substances as pure substances or mixtures. A pure substance is defined as only one type of thing. Now what that thing is up for debate. It's either atoms or molecules. We also refer to molecules as compounds, substances. I'm sure there's some others that I'll use throughout the lecture and throughout the course. Mixtures are composed of two or more things. That can be two or more atoms if they're not bound together. That can be two or more molecules. That can be one type of atom and one type of molecule. I could have an atom of helium and a molecule of oxygen. That would be a mixture of gases. It's kind of up for debate how things are arranged, but we'll get to that in a second. So when we classify pure substances, the most simple way to classify something is an element. An element is a single type of atom. Now that can be a single atom. Any single atom is always a pure element. Or you can have a conglomerate of the same type of atoms. A whole bunch of iron atoms, a whole bunch of gold atoms, a whole bunch of oxygen atoms. Now, that's not to get misconstrued with a whole bunch of oxygen molecules. Oxygen molecules and oxygen atoms are different. And we'll get into that later. So an example of this, other than what we've given, is a balloon filled with helium. Helium is a pure element that takes on an atomic state. This is true of all the noble gases. This is a classification of chemicals on the periodic table. It's the very last row on the periodic table. That all kind of take this behavior. They're all single atoms that are gases. They don't really interact with other things. Compounds can be pure as well. So if we have a mixture of atoms in definite proportions, water, H2O. No matter where you go in the universe, water is always water. It's always two hydrogen atoms arranged in a bent configuration around an oxygen atom. If we only have water, that can be a pure substance. Now, what we drink is not pure water. There's a bunch of minerals and salts dissolved in that. And so our water would be a mixture of substances. And we'll tell you how we classify that once we get to mixtures. So water, we have only water atoms in here, or water molecules. We have hydrogen and oxygen atoms in here in a 2-to-1 ratio. But we only have water, no dissolved salts, no nothing else. We would call this a pure chemical, or a pure compound, a pure substance, a pure material. If we want to classify mixtures, we can classify them as either, well, okay, sorry, I'm jumping ahead. Classifying mixtures versus pure substances, like we said, pure substances only contain one type of thing, whether that's atoms or molecules. Mixtures contain a mixture of things at any given proportion. So if we have a pure substance, even if there's different atoms, if they're in defined portions like water or octane or carbon dioxide, that can be a pure compound or a pure chemical. If we have a mixture of atoms and chemicals at any given proportions, that guarantees we have a mixture. Classifying mixtures, we can either have what we think of as pure mixtures or not pure mixtures. We have heterogeneous mixtures, which have different phases. You can see a difference in the phase. Oil and water, you can see two distinct layers. Or homogeneous mixtures, a pure mixture, so to speak, like our drinking water. You can't see any difference of phase. Everything is perfectly dissolved. And from inspection from across the room, if you had seawater and regular water, you wouldn't be able to tell. Both of those are mixtures. But if I had oil and water, that's a heterogeneous mixture. If I had sand and water, you can see the difference in the phase. Those are heterogeneous mixtures. Air and seawater is an example of a mixture. We would call this a heterogeneous mixture. It's kind of hard. I won't ask you about gases because gases are kind of arbitrary. Most gases are invisible to our naked eye. Oxygen has a very beautiful blue color, but you would never know that because, or you likely wouldn't know that because you've probably never seen oxygen condensed into a dense enough state like a liquid or a solid so that you could actually see what color it is. But we would call air and seawater heterogeneous mixture. There's a phase interface where the sky and the water meets. So here's a real good picture or slide to take a picture of to note. This is kind of everything that we've gone over. So matter can be broken up into pure substances and mixtures. Pure substances are either elements or chemicals, compounds, molecules. Mixtures can be either homogeneous, fully dissolved, we can't really tell a difference in the phase, or heterogeneous, where there's a separation of phase. Sand and water, oil and water, these would be heterogeneous mixtures. So, to put that in word, we have pure substances and mixtures. Substances can be elements or compounds. Mixtures are either homogeneous or heterogeneous. All right, so now we're going to talk about chemical and physical properties and chemical and physical changes. So one thing I want you to note is that properties are the ability to do something. Changes is the activity that the property describes. So we'll start with properties. A physical property is some type of ability displayed by the physical state. So this is going to be, melting points, boiling points, vaporization, basically changes of state, smell, things of that nature. Chemical properties are their ability to undergo chemical changes, flammability, corrosivity, oxidation, reduction, things like that. So a physical property is something that is distinctive to the physical state. So odor is related to the particles in the gaseous state. And so the boiling point is the temperature at which something has to reach in order for it to change from the gas to the liquid state, or from the liquid to the gas state. Condensation would be from the gas to the liquid state, which also occurs at that temperature. So here's a couple examples of physical properties. Now remember, Boiling a liquid, that would be a physical change. We're just describing the ability, or we're just describing the properties. So a chemical property would be the ability to do some type of chemical change. So rusting, you know, is an actual chemical change, but being able to rust is a chemical property. Flammability, like I mentioned, is the ability to be burned or the ability to be oxidized. Corrosiveness, toxicity, acidity, these are all chemical properties. Chemical properties can be reiterated in a whole bunch of different ways that say the same thing. It's often depending on what your particular discipline is interested in. So, chemical and physical changes. So, if I'm boiling water, this is a physical change. There is no chemical change occurring here. However, if I pour this water onto the metal and then it starts to rust, that would be a chemical change. So boiling is the most common physical change that gets misconstrued as a chemical change. The big things to remember is that a physical change, you can always recuperate what you started with. If I boil water, that water doesn't turn into something else. That water goes somewhere else. It goes from the liquid phase to the gaseous phase. So if I'm boiling water on my stove, the water doesn't just disappear. It doesn't cease to exist. It recondenses on the hood fan above my stove. If I'm taking a shower, the water that turns into steam doesn't just turn into nothing. It recondenses on the mirror outside the shower. If I can recapture what I started with, it's most likely a physical change. If I can't recapture, if I do some type of chemical change, like burning butane, burning a fuel, I can't get that fuel back. Once I do the change, once I burn it, I get something else out of it. Chemical changes result in chemical reactions, which we're about to talk about, and that's where the actual atoms rearrange themselves. They're no longer bound in the same way they were originally, so you can't reclaim those. There are some examples of reactions that we call reversible, where you can push them one way and then return them back to their start. But those are a little bit more rare or require special conditions. If you don't just naturally able to reclaim whatever you started with, you're probably dealing with a chemical change. If you can reclaim what you started with, like boiling water, you can eventually reclaim that condensed steam. You're dealing with a physical change. All right, so physical changes of state. If you're dealing with a change of state, that's going to be physical. If you're going to alter the physical state, crushing it, smashing it, cutting it, ripping it, those are going to be physical changes. If you do something that changes the chemical nature, if you change what atoms are bonded to which other atoms or which chemicals are present, that's a chemical change. So, kind of re-saying the same thing. Melting is just physical. It's not changing the chemical composition. It's staying exactly the same. The same amount of atoms in the same arrangements are in the same places. But in a chemical change, we rearrange the arrangement of atoms or completely separate the bonds. It depends on what type of chemical change we're doing. So we've been talking about chemical changes a little bit now. How do we formally define chemical changes? Well, that's what we have down here. We have some type of reactants, which I typically call starting materials. It's a little more intuitive to hear starting materials instead of reactants. Products is what is produced throughout the reaction. And so we only really have products as something, maybe the end products, things like that. It's a little more of an intuitive term, where sometimes we say reactants and it takes us a second to remember what that is. I like to use the term starting materials. We can call any chemical a reagent. We typically only talk about chemicals as reagents when we're doing chemical changes or chemical reactions. So reagent is a new term for a molecule. So here's an example of a chemistry apparatus that would do a physical change. So down here we have some liquid that is being heated by a Bunsen burner or by a flame. That liquid is going to heat until it reaches its boiling point. Then it's going to turn into a gas or a vapor. The steam will come up until it hits the dead end of the stopper. It'll flow to the next place it can. This condenser is cooled with water, so there's water flowing in this inlet and out this inlet, so it makes sure that this entire tube stays really cold. That's going to recondense all of the gaseous steam up here back into the condenser, which will eventually drip down into this receiving vessel, and you get a pure liquid based on its boiling point. If you separate things that have very similar boiling points, this doesn't work very well. This little nipple outlet port is for a vacuum. So if you had something that you had to do under a vacuum, you could attach this to a vacuum apparatus and pull vacuum through that point and still collect the liquid. There's a tube that flows directly down to the receiving vessel before this vacuum joint. It's jacketed is what we would call it. So we'll see that in the chemistry lab. Here's another apparatus that we'll set up ourselves. So we'll have some type of funnel. You can put a filter in here and you can separate things physically. So this is great for separating things based on their physical state. So previously we were separating things based on their boiling point, a physical property. Now we're separating them off their physical state, so liquids versus solids. So you could dissolve one solid in a given solvent that the other doesn't dissolve in, and then you could pour it through this filter. Depending on how fancy your filter is, you might not even need to dissolve everything. If you have a charcoal filter for your water bottle or anything like that, one of those smart straws where you can drink out of a muddy puddle. They have very complicated filters that you can flow a mixture of nasty stuff through, and it only extrudes the pure drinkable water at the end. So we're going to get into the law of conservation of mass and energy now. And so these laws are basically just reiterations of the same fundamental property. Energy and mass are fundamentally related. Albert Einstein did this in his famous E equals mc squared equation. Energy is equal to mass times the speed of light squared. And so you can convert mass and energy. This is the whole idea of nuclear energy, whether that's fusion or fission. We'll get into that later in the course if we are interested. So the law of conservation of mass says that matter can neither be created nor destroyed in an ordinary chemical reaction. So we have nuclear chemical reactions. This is where we fuse mass together or break mass apart to release a whole bunch of energy. So we won't really talk about that. That's not the focus of this class. So you never change the amount of mass that you're dealing with. You never change the amount of matter. So whatever matter you have or however much mass you have in the starting material is how much mass or matter you'll have in the products. So the sum of the masses of the reactants will always be equal to the sum of the masses of the products. So if I have 58 grams of butane that is exploded or combusted in 208 grams of oxygen, that'll give me different things than I started with. I won't have any butane or oxygen to start with, but I will now have 176 grams of carbon dioxide and 90 grams of water. The masses of these sum up to be identical. That's because we can't create or destroy matter, nor can we do that to energy. We can only just transfer forms. So we transferred all of the carbon and hydrogen in butane to be the carbon and carbon dioxide and the hydrogen and water. The oxygen was split apart and became part of the oxygen and carbon dioxide and part of the oxygen and water. We rearranged all the atoms, but we didn't add or subtract any atoms. The total number of atoms in butane and oxygen is equal to the total numbers of carbon dioxide and water. This is why each sample has a similar mass of 266 grams. Matter is always conserved. Energy is the same way. We're going to deal with it a little bit different. Energy, we're either going to add energy into a reaction to get it going, or a reaction is going to occur and energy is going to be released. We can neither create nor destroy energy. We can only convert its form. We can either supply energy and store it in chemical bonds, or we can release it from chemical bonds and generate energy or work. We're not really going to use work very much in this class, but it is a fundamental relation to energy. So, like we said, the law of conservation of energy is neither created nor destroyed. It can just be converted forms. The total amount of energy is constant. So, we can do something like this where you have a dam. The total energy is the same. It never changes, but the amount of kinetic energy and potential energy shifts. We have water that's up at the top of the dam. It has a very high potential energy. If we let it flow through the dam and turn the cranks that generate electricity, it'll change that high potential energy for a high kinetic energy, which then we harvest for electricity. After it flows through the dam, it then has a low potential energy, but it expended a whole bunch of kinetic energy during that process. That energy is not lost, it's just converted. So it's converted from a high potential to a high kinetic, which is then harvested to generate electricity. It's just a conversion of energy. So we have electrical energy. We'll sometimes talk about electrical energy in chemistry. We have thermal energy. This is a very important part of chemistry, as well as chemical energy. Thermal energy is associated with the random motion of objects. So the more thermal energy they have, the faster they move. The hotter something is, the faster the particles are moving. So if particles are moving around really fast, they can collide. If they collide together more often or with higher forces, they're more likely to undergo chemical reactions, which either generate or release or generate or store chemical energies. Sometimes this thermal energy will be stored in the form of chemical bonds. Sometimes this chemical energy will be released in the form of thermal energy. So we are most commonly going to use the joule. The joule is the SI unit for energy. However, the most familiar unit of energy is the calorie. Now, the calorie we have here, that's the amount of energy required to raise the temperature of water by 1 degree Celsius, 1 gram of water by 1 degree Celsius, is not the calorie that we're familiar with. We're familiar with the kilocalorie, or calorie with a capital C. We don't often call it the kilocalorie, but that's what it actually is. You know, it's 1,000 times what the little c is. So if you see big C, that's the nutritional calorie. That's a kilocalorie. We won't use kilowatts per hour. You might see it in the book, but that's about it. Primarily, we'll be using the. Sorry about that. Primarily, we'll be using the joule or the kilojoule. However, the kilojoule and the calorie are related by the specific heat of water, which is a specific heat is another quantity we'll talk about right now. But essentially, 1 calorie is equal to 4.184 joules. I think that's right here on the next one. So we have 1 calorie is equal to 4.184 joules. A kilocalorie, or the calorie that we're familiar with, is equal to 1,000 smaller calories. And then you don't need to be worried with the kilowatt hour. So if we wanted to figure out how many joules were in a candy bar, we could go look at the label, see how many calories were in there. We know that the calories on the back of the label is kilocalories, so we would have to do a 1,000 to 1 conversion to get to regular calories. Then from calories to joules, we would use our conversion factor here, making sure that whatever unit is in the denominator cancels out with the previous unit. And so we would get something that looks like this. 250 calories, kcal, times by 100 calories over 1 kcal, times 4.184 joules over 1 cal, to make sure that we only have joules at the end of the day, and this would be our answer. So even a small candy bar has a whole bunch of joules in it, and that's one of the reasons why the kilojoule is a pretty familiar unit, or a pretty favored unit. So just another way to illustrate that energy just is converted from form. So this is not a chemical change, but a physical change. We're taking some type of anvil that has been raised to the top of the building. It's gained some amount of potential energy through being put on the top of the building. When we drop it, that potential energy is actively being converted to kinetic energy. Once it slams into the ground, all of the kinetic energy is dissipated. Now, some of that energy causes deformation of the cement and the block. Some of it is directly converted into thermal energy. Some of it is used to push the earth down, although the earth is so massive that the amount that it's pushed down is not even detectable. If you're dropping something 10 kilograms, 20 feet, the earth that weighs, maybe 100 billion times more than this, I have no clue. It's not going to have a meaningful impact. But energy is just transferred, it's not lost. So high potentials tend to go to lower potentials. And if you have instability, that change is going to happen readily. So we have some chemicals that are what we call shock sensitive. TNT is a very famous shock sensitive chemical. It is actually very stable. It has a high potential energy. There's a lot of chemical energy stored in the bonds of TNT. However, you can hold it in your hand. It's perfectly fine to carry around with you. The problem is once there's some sort of stimulus, a shock or an ignition, some type of detonation, the TNT will react explosively. And so usually you have some type of detonation core. The TNT will react after the initial reaction is there to kind of jumpstart it. So this gets us into what type of reactions we have. So TNT has a bunch of energy stored into it. Once it reacts, it lowers its energy and releases a whole bunch of energy that was stored in its chemical bonds. We call this an exothermic reaction. We have exothermic and endothermic reactions. In general, exo means to leave or exit. Endo means to receive or to enter. Exothermic, endothermic, exergonic or endogonic if you've done some biology classes. So in an exothermic reaction, we have a whole bunch of energy stored in the starting material or the reactants. That energy is released by some sort of reaction, and the products have much lower energy. And that energy is part of the products, essentially, if we were to look back at the chemical reaction. An endothermic reaction is the opposite. We need to apply some sort of energy to these reactants so that they can form the products. This energy is absorbed and stored in the chemical bonds of the products. Whereas in an exothermic reaction, the chemical energy stored in the bonds is released, and then the byproducts exist along with that released energy. Whereas in an endothermic, reactants come together, absorb some amount of energy, and then make new products that hold that energy in them. So we mentioned this a little bit before, but temperature is directly related to thermal energy, and thermal energy is internal energy, essentially. It's how fast or how readily things are moving. Basically, the hotter something is, the faster the particles are vibrating or moving around the liquid. So temperature is a measure of the thermal energy, how much thermal energy is in an object. Heat is different. So typically, as normal people, we use heat and temperature interchangeably. However, heat is the transfer of thermal energy. Heat is the transfer of temperature, so to speak. So temperature is the measurement of thermal energy, how much thermal energy is there based on some type of scale. Heat is the transfer of thermal energy. So related to each other, but different entities. So we have a couple different temperature scales. We're probably most familiar with Fahrenheit. Water freezes at 32, boils at 212. Room temperature is anywhere between 65 and 75 degrees. The Celsius scale, so the Fahrenheit scale is kind of how do people feel about water. 70 is pretty comfortable, 100's a bit ridiculous, 0 is freezing. When we have the Celsius, it's exactly how water feels. 0 is freezing, 100 is boiling, room temperature is just some random number. It's somewhere between 20 and 25 degrees Celsius. Kelvin is the scale that we want to use for science. The reason for this is Kelvin is the Celsius scale, scaled so that it has an absolute zero, so that the temperature scale starts at zero and then goes up from there. There is a top end of the temperature scale, but that's not really important, and doesn't really, yeah, it doesn't have much importance to physics or even chemistry, especially chemistry. So absolute zero has a lot of physical meaning. At absolute zero, all molecular motion stops. It doesn't virtually stop. It does stop. Now, there's some fundamental theoretical things that this relate to that we can talk about if you're interested in personally. But it doesn't matter in this class. We just want to know that absolute zero exists. That's where all molecular motion stops. And the Kelvin scale is based off of that because calculations need to have a zero. Zero has to have a meaning in mathematics. And so having a temperature scale that starts at zero makes calculations much more simple and straightforward. So water freezes at this nonsense temperature and boils at this temperature. The more important thing to remember is remember the Celsius points and know that the difference between Celsius and Kelvin is 273 degrees Kelvin or Celsius. So here's a comparison of the temperature scales. So water boils at 212 Fahrenheit, 100 Celsius, or 373 Kelvin. Absolute zero. If we didn't use Kelvin, we'd have to use these awkward, minus 459 and minus 273 Celsius. We'd have to use those as correction factors in every single calculation we did. That would be very cumbersome, and I know I would make mistakes, so we don't do that as a community. We always just use the Kelvin scale. So here's a conversion factor that will be given to you on your exams. You should be familiar with how to rearrange them. If I wanted you to have something in Fahrenheit, you'd have to be able to use this Celsius equation and rearrange it. Multiply each side by 1.8, then add 32 to each side to get Fahrenheit equals 1.8 Celsius plus 32 degrees. I guess the book makes a deal about this. I don't know why people make a big deal about this. Kelvin doesn't have a degree sign. Celsius and Fahrenheit do have degrees. It's just Kelvin. It's not degrees Kelvin. It's degrees Celsius, degrees Fahrenheit. It's just Kelvin. I got trick questions on that when I was in my undergrad. I won't be doing that, but, something to remember. So, temperature changes. How do we talk about temperature changes or heat change? We have to use some new factor that basically says, how does every material interact with heat? And so we have specific heat capacity. So specific heat capacity is the quantity of heat required to change the temperature of 1 gram of the material 1 degree Celsius. So specific heat capacity is typically going to be, at least when I give it to you, will be in joules per gram degree Celsius, because we always use Celsius even though we do calculations with Kelvin. Actually, I'll probably give you joules degree or joules per gram Kelvin, not degree Celsius. We do use Celsius most oftenly, but like I said, I want to get you guys in the habit of using Kelvin for calculations, so that'll be how I give it to you. However, this is the most common way that you will see specific heat reported. So here's just a whole bunch of specific heats. What you notice is that metals tend to have really low specific heats. This means they transfer their temperature very quickly. Water has a very high specific heat. It takes a lot of energy to change the temperature of water. This is true of insulators as a whole. So, like I just pointed out, water has the highest specific heat on the list. So changing the temperature of water requires a lot of energy. It requires a lot of heat. But if I want to change the temperature of aluminum or some other metal, it doesn't take that much because of certain physics that we don't really care about. So one thing you can think of is, if you're boiling a pot of water, the metal gets hot before your water really ever does. That's because the metal conducts heat so much faster than the water. Also, the metal's what's directly touching the heating element, but, That's just a contributing factor. So we have this equation for heat transfer. Q equals mc delta T is how we usually refer to it. So heat is equal to mass times the specific heat capacity of the thing that you're talking about times the temperature change. So we mentioned that Celsius and Kelvin have the same slope, or that they're based off the same change, but Kelvin's just shifted by 273 degrees. Because of that, you can get away with using Celsius. However, for every other temperature calculation we do in this class, you won't be able to get away with Celsius. You'll have to use Kelvin. So that's why I'm trying to get you guys in the habit of doing Kelvin now, rather than using Celsius and Kelvin interchangeably here and then getting screwed over later down the road when you have to use Kelvin for gases and solutions. So, joules, grams, temperature is in either degrees Celsius or Kelvin. So our specific heat capacity has to have all of the opposite units. So heat capacity is being multiplied by mass and temperature, and it's set equal to joules. So at the end of the day, mass times specific heat times temperature just gives us joules. This is essentially, a unit conversion placeholder. So if you're not familiar with this delta T, delta is just how we represent the change of some variable. So the change of some variable is the difference or the subtraction of its final condition from its initial condition. So the final temperature minus the initial temperature is equal to the change in temperature, or the delta of the temperature. We refer to this as delta T. So we could do a quick problem where we had some gallium. We know that gallium melts at 29.9 degrees Celsius. So you can melt it in your hand. Your hand is, about 30 something degrees Celsius, depending on how warm it is, how warm you are. But, body temperature is about 36, 37 degrees Celsius. So plenty hot enough to warm this up to its melting point. If I had 2.5 grams of gallium, how much heat would it need to absorb from your hand to raise from room temperature to its melting point? Given the specific heat, we could, basically take the change in the temperature, so 29.9 minus 25, multiplied by the amount of mass, multiplied by the specific heat, and we would get just the amount of heat required to do that process. So we have Q equals mc delta T. We were given mass. We were given the specific heat. We could calculate the change in temperature based on the temperature final minus the temperature initial. And if we plug that all in, we would see that our units cancel out and we would have, this amount of joules. However, if we look back to our starting conditions, some of these have 3 significant figures, some of them only have 2 significant figures. At the end of the day, we only had 2 significant figures in the starting mass. We should have had 3 significant figures here because we had 3 significant figures. Actually, no, we should only have 2 significant figures here because we're doing addition rules. So we would have cut off at the tens place, but we no longer have anything in the tens place. We cut off at the tenths place. We don't have anything in the tens place, so we'd only have 2 significant figures. At the end of the day, we need to round to 2 significant figures because this is a multiplication type equation. Every one of our variables is multiplied together, so we'd have to use our multiplication rules for significant figures. So that is chapter 3. We can go over some of these calculations if you're confused about them in lab. There's not going to be a lot of this. It's mainly just how do we talk about things. So matter can be defined as solids, liquid, and gases. Solids can be refined a little bit more as amorphous solids or crystalline solids. Those crystalline solids have a crystal lattice that has that repeating arrangement of different planes or different molecules in a repeating order. Amorphous solids have just a random arrangement or agglomeration of particles or compounds or whatever we're talking about. We can classify matter in a couple of different ways. Most simply, we can classify things as pure substances, which are elements or chemicals, compounds, molecules, or we can classify them as mixtures. Mixtures can be broken up into homogeneous mixtures, basically things that are fully uniform. fully dissolved, or things that are heterogeneous, things that have separation of phase, oil and water, sand and water, things like that. A homogeneous mixture would be, a bottle of water. The water in there has minerals in there. We talked about physical and chemical properties. These just describe the ability to do some type of physical or chemical change. Chemical changes are characteristic by that they don't change the chemical. Whatever chemical you started with is whatever chemical you finish with. A chemical change is defined by a rearrangement of the atoms and molecules after some type of activity or action. We had the law of conservation of mass, which allowed us to calculate for missing masses of reactants. So if we had, a solid and a liquid we mixed together that caused a chemical change and some amount of gas bubbled out of it, we could figure out how much gas bubbled out of it by weighing, the chemicals before and weighing what we had afterwards. The difference between those two would be the amount of gas that left the product. So we can always balance the reactants or the starting materials and the products of any chemical reaction. Energy, likewise, is always conserved, so we can do similar things. Energy is not created nor destroyed, it's just converted forms. Either we add energy to a reaction and we store that energy in chemical bonds, or we break chemical bonds and release energy from that reaction. These are exothermic and endothermic reactions. Exothermic reactions release energy, endothermic reactions absorb energy. And then we talked about our temperature and heat transfer, specific heat capacity, using that Q equals mc delta T. Specific heat is just the amount of energy required to change the temperature of 1 gram of material by 1 degree Celsius. So that will be different for any type of material out there. You won't have to memorize those. I'll give those to you. Same with the conversions from the different temperatures and units. All right, so we talked about a whole bunch of stuff, but most importantly, we want to remember physical properties of states, solids, liquid, and gases. Classifying our matter, is it pure? Is it a mixture? Is it homogeneous, heterogeneous? Is it an element? Is it a compound? Physical versus chemical changes and properties. I'm not going to split hairs over whether it's a physical change or whether it's a change or a property. I do want you to realize that properties explain or describe what changes do. They are, two sides of the same coin. And then we have heat calculations as well as the conservation of mass calculations. So if you have any questions about this, please feel free to reach out to me in lecture or office hours, and I will talk to you guys in lecture 4.